utilizing people in the first row here. Body in the front row? Okay, that'll work. So, let's back up on the graph for a minute, sorry. Let's get some values first. Alright, so I need some heights of the people in the front row. Andy, how far?
5 seconds.
67? Okay. Yeah, you're afraid to say your height? Okay, we'll see. 5'2". There's nothing wrong with 5'2". Bill, what do you think?
Shorty.
6'3". Okay. Oops, I just What's that? 6 foot. 6 foot? Alright, so these are those conversions into inches. And again, what I want to do is I want to measure the standard deviation for this collection of data. Okay, so we're just going to calculate standard deviation, and we're only going to do this a couple times. I'm not going to ask you to calculate standard deviation over and over again. I'm going to ask you to do it a couple times, maybe once on a quiz, probably never on a test. Again, I don't want to know whether or not you're a human calculator. I want to know if you understand what the standard deviation is and what it measures. Okay? So, first things first, we need to find the mean. Okay? What's the mean of these 5 values here? Okay. The average here, X bar here, 69.2. You're not that sure. Oh wait, there's our average. So now what we're going to do is we're going to calculate all of our deviations, so our X minus X bars. So let's go ahead and do that. Alright, so middle column, start reading off values. 67 minus 69.2. Negative 2.2. 62 minus 69.2. 70 minus 69.2. 28. 75 minus that. 5.8. And then the 72 minus that. 2.8 there. Okay, so there are all of our deviations. Next thing we're going to do is we're going to calculate our squared values. I know, it's fun. Math class is fun. Alright, so 2.2 squared is 4.84. 7.2 squared. 51.84. 0.6 squared.
So you're not allowed to arrange it?
What's that?
Never mind.
Sure.
Yep.
Okay.
Wait, how did you get 51.84?
51.84?
Wait, no, never mind. I'm totally
Whoa, sorry, whoa. Yeah, sorry.
I'm putting the wrong thing.
It's alright. The next one here, the 5.8 squared, is the 33.64. My calculator told me I was trusting you. And 7.84. Alright, so those are all of our deviations squared. Now we're going to add them all up. 3.64 plus 0.64. 4.84. If we add all of these up in the last column here, we get 98.83. Cannot be right. Oh, sorry.
Why can't it?
Because these are all even. This better be even as well. Okay. It should be 0.80. There we go. Alright, so that's the sum of the deviation squared. Now, if we go back over here to our formula, okay, the next thing we have to do to get to that standard deviation is we have to divide this value by what? In this case, we're going to divide it by 4. So that gets us to 98.8 over 4. We're looking at 24.7. We're almost there again. Now, according to our formula, we have to take the square root of this. So we take the square root of that. And what we get is that our S comes out to be about 4.97. Okay. So this value, this 4.97 here, is telling us that on the average, if we were to take one of these heights at random and do that a bunch of times, on the average, those values would differ from the 69.2 by roughly 5 units. Not too bad, okay? But that's what this tells us. Okay? Now, suppose I was to take a bunch more heights and throw them into this collection. What do you think would happen to this S? What do you think happens as I get more and more values? Well,
Depending on whether they're higher or lower.
okay, so for example, Travis over here, you're what, 6'8"? I don't know, 6'4"? I was pushing it better down. Play basketball, I figured 6'8". Let's take that. Alright, so we take Travis's and we throw it in here, he's 6'4", that would be 76 inches. Okay? Alright, that maybe raises it up a little bit, right? Adding the 76 in, 76 is above our average, and so that's going to cause our data to be a little bit more spread out. Okay. So we would expect by throwing in that value that our spread is going to increase a little bit more. Okay. All right, well then I'm coming over here and I'm going to say, all right, Kim, how tall are you, Kimberly? 5'4". Okay, so 5'4", that's going to be down at 64 inches. That's below the mean. What's that going to do? Well, you know, that's sort of going down a little bit, but at the same time, it's going to cause our average to go down a little bit. And so, you know, maybe it's going to balance out. We have Travis's and we have Kimberly's in there. Maybe those two are going to balance out, and they're going to cancel each other out in some way. As we increase the number of data values we have here, one thing that you should see start happening is, at some point, our standard deviation isn't going to be changing very much anymore. Okay? We start getting enough values in here, our standard deviation is going to stay pretty constant. Okay? So when we have lots of values to deal with, lots of values of standard deviation, adding one or two more after that isn't going to change our standard deviation very much. But if we have very, very extreme values, suppose someone came in and said, yeah, I'm 3 foot tall. Someone comes in at 3 foot tall, you're looking at 36 inches, that's going to throw this off by a lot, right? Because that one value is so far below all the other ones. It's going to cause this mean value to decrease by a considerable amount, which is then going to cause the difference from all of our other data values to increase by a lot, which is going to cause our standard deviation to decrease. Okay? So when we're looking at distributions of data, as we look at our graphs here, and typically when I start working with standard deviation, I try to use picture graphs as opposed to like histograms or something like that. But the same principle holds for histogram type graphs as well. As we look at the values of our standard deviation, something like that. Put one more in here. Okay. These three graphs have basically the same measures of center. The measures of centers on these graphs are basically the same. The only real way that we can distinguish between them is to talk about how spread out the data is. So if I give you values of standard deviation, say 15, 8.1. If I was to give you these three standard deviation values and ask you to match these standard deviation values with the graphs here. Okay. Take a moment and think about that. Figure out which of these goes with each of these graphs. And then we'll take a look at some other properties here. But if you were to try to match these up, which of these graphs would you say would have the standard deviation of 15? In this particular case, the red one here has the largest standard deviation because it's the most spread out. You'll notice that the data is spread out very far. There's no big bump in the middle. There's a small bump, but more or less, the data is sort of spread out pretty far. Okay? The 8.1 then would go to which graph? The 8.1 would go to the blue one, being sort of the next least, or the next spread out. And then obviously, process of elimination leaves us with the last one being our graph in black. Okay. So, increasing or decreasing the standard deviation is just a matter of affecting how spread out our data is. Alright, so what are some properties that we can look at in relation to the standard deviation? Okay. There's a couple of really fundamental properties we need to talk about. The first one is that standard deviation is always positive, or I should take that back, it's always non-negative. Okay? So I can never have a standard deviation of -1. What does it mean to say the average data value is -1 units away from the mean? I don't know how to, I don't have a ruler that measures -1 units. Okay? So standard deviation is never going to be a negative value. Okay? Standard deviation can be equal to 0. In your words, what does it mean to say that the standard deviation is 0? What does that mean? What's that? You sure? It's flat. Not necessarily, well, depends on what you mean by flat. Flat to this way, flat to this way. No, not flat down. Flat up, yeah, there you go. If the standard deviation is 0, you go back to the definition of standard deviation. Remember, standard deviation is the average distance away from the mean. If the standard deviation is 0, that means that the average distance from the mean is 0, which means what?
They all have the same.
It means that if you look at the graph is a single vertical line. In terms of our data, that means all of our data values are the same. Okay? Standard deviation is 0 when all of the data values are the same. We talked about the other property, which I'll just write it here again. Larger S leads to larger spread. All right. So those are our basic properties of standard deviation. Okay. Standard deviation is going to be a central theme throughout most of the course. So make sure you understand what it does, what its properties are, and sort of use those properties to sort of identify things about graphs. So let's look at a quick example. And again, this example, I'm not expecting you guys to all sort of have 100% fluency on how to find this, but this is just sort of an example. So if I told you that the test scores, actually we'll go quiz scores. The quiz scores here were skewed right, or sorry, skewed left, with a mean of 8.58. Okay, which of the following values would you think could be standard deviation? So here are 4 standard deviation values, 4 possible standard deviation values. Our quiz was again out of 10 points. Based on this information, which of these values here do you think would be the standard deviation for this collection of data?
C.
We can identify why some of these are not valid. The S equals 0, for example, well, if all of the scores had the exact same value, there would be no way we could have a mean value like this, because I didn't give an 8/100th of a point to